tells me that it's just never going to happen. Well, it looks different. Somebody there in Maxwell? Looks like we're looking at the teacher's desk instead of the students, but I suppose if they're going to be there, they'll show up. Okay, so last time we met, we got about halfway through chapter 2, and we're going to get the rest of the way through it today. Try to get done with as much of the bookwork as we can here, beginning the semester. And actually some fairly interesting topics to cover today, which is good, considering that things coming out of textbook are often quite boring. There's so many boring things to learn in so many different classes that you just feel like you're waiting to get to the exciting part of it. But today is Friday the 4th, and we're supposed to be going through the last 3 sections, 10, 11, and 12, but we're actually going to be back in, I think that we ended up right around, we started talking about the different disciplines, the different engineering fields, and so that was all the way up to 2.5, and we kind of got on to a couple of other things, but I want to go back to the different fields of engineering and cover that a little bit better. Just to give us an idea of what we're facing here, let me just type this in here and see what it brings up. It's always kind of interesting for this particular, the list of engineering branches. Here they start with this, they've got these 6 different branches of engineering they call chemical engineering, civil engineering, electrical engineering, mechanical engineering, systems engineering, and interdisciplinary engineering. And this is by no means the end of the list, really, because we drop down into, let me make sure I'm recording here, it looks like I am, that's good. Drop down into what they call chemical engineering, and then they break it into biomolecular engineering, materials engineering, molecular engineering, process engineering. And that is by no means the end of those lists either. You can break these into several different materials engineering, metallurgical engineering, ceramics engineering, polymer engineering, crystal engineering, biomaterials. Molecular engineering has a lot of different ones as well, but over here in process engineering, petroleum refinery, plastics engineering, paper, textile, and there are far more than that even in process engineering actually. Manufacturing engineering is a big part of process engineering actually, in general. Then you go down to civil engineering and the same thing happens here. In civil engineering they go to environmental engineering and then they show these 5 different ones, but there's far more than that. And geotechnical and structural and transport and water resources. You go down to electrical and there's computer rather, electrical, optical, power, and there's more than that. You get all these over here and they break down into many, many others. And down in mechanical, you have acoustical. And the funny thing about these fields is that there's a mosquito in here. I hate mosquitoes. Oh, mosquito. The interesting thing about this one is my brother just got his PhD in mechanical engineering, but he was an acoustical engineer. And he actually does something different than that even. His specialty is actually in the thing that I think that he's doing now is high-speed photography or high-speed something for, I don't know exactly what he does. He works for a contractor that works for the military, so he can't really tell me what he does exactly. But you don't necessarily have to go off and do something in the field that you get your degree in. you'll get, in a lot of these degrees, you're going to get such a broad experience that you'll have a lot of options. So, and, you know, the options not only include the different jobs, but different places you get to live. He gets to live in Rhode Island, which is a beautiful place on the eastern seaboard. Very interesting place in a lot of different ways.
Good old human.
Okay, so then interdisciplinary, they talk about aerospace and agricultural engineering, which of course is huge in this state. We have agricultural engineering, which includes biological engineering, biomechanical engineering, bioprocess engineering, biotechnical, even throw in biomedical if you wanted to, ecological, in energy, environmental, food, forest, health, natural resources, machinery systems, pharmaceutical information. Machinery systems engineering is actually a huge thing that UNL does. Most people aren't aware of this, but every time a tractor company builds a new tractor and tells everybody all the great things about their tractor, UNL tests that tractor to make sure that it meets the standards that they say that it is. And they put out their own report. So the company puts out one report, UNL puts out another report, and if they match, that's good. If UNL's report's better than your report, that's even better. If UNL report's worse than your report, that's bad. And from year to year to year, people are looking at UNL's reports on people's tractors, and that's how they decide which tractors to use. And it's a big part of their school. They have an entire research section devoted to it, and a huge, they have a big track where they do their testing, where they pull things and they push things, and they'll see what kind of performance they can do. So lots of other kinds of cross-discipline engineering, where you're using a lot of different types of engineering all in one field. And I mean, here's another one that's pretty relevant to us here in North Platte, railway engineering. And railway engineering is something that's a job here in North Platte. There are people that have engineering backgrounds, engineering degrees, engineering experience, and they're getting hired not directly by the railroad usually. Usually the railroad contracts this work out, but they're working for companies like GE. GE provides all the engines for all the, well, not all the engines, they provide all the motors for the engines. So if you're not aware, a diesel engine on a locomotive is actually run by electric motors. The electric motors are connected to the drivers, the wheels that that move the train, and those motors are connected to batteries, which are connected to generators, which are charged by the diesel engine. And people think, oh, that's not very efficient, but that is efficient. That's exactly how the Toyota Prius works. The Toyota Prius has electric motors on its wheels that are connected to batteries, that are connected to generators, that are connected to a gasoline engine. And it's a very efficient way to do things as long as you have good batteries and good generators, a good generating system. If you don't have those two things, you're screwed. But it's quite true. The real reason that electric cars have not been a reality until today, most people say, well, it was Detroit was squashing them out and politics were squashing them out. But the real reason is that we have not been able to have batteries that were good enough so that they were small enough and light enough to be in a car. All the electric cars before the Prius were so heavy. Well, not all of them, but most of them. A couple of them just before the Prius were quite good. But pretty much they were all so heavy, they hold such a low charge that they were just impractical and too expensive. But the other big problem is that controlling the recharge and the discharge of the batteries was very difficult. Because if you don't recharge them just right and discharge them just right and keep the charge balanced across the entire battery bank, the batteries charge and discharge each other, and you lose a lot of your energy that way. In fact, you can even ruin batteries. And so this is a huge deal in engineering, fixing this problem. For the past 40 years, they've been working on this problem. They finally figured it out. And actually, the railroad played a big role in that. The technology that was developed by the railroad, as they figured out how to do it, was adapted for cars, and over time they were able to get small enough batteries to do it in cars. And good enough batteries is the big deal. And laptops, computers helped with that, because the need for small lightweight batteries drove the battery industry into making newer lightweight batteries, and they used those kind of batteries in cars. So lots of different engineering things can all work together and make big changes happen. But that is something that is very much part of our economy here. General Electric and other companies hire engineers to do railroad work. The difference between working for the railroad and working for one of those companies is huge. If you have any experience working for the railroad or family working for the railroad, you know that between dealing with the railroad management and the unions and everything else, it's a major headache, a major pain in the neck, and you have to essentially dedicate your life to navigating this mess. And it can be a good life if you're willing to dedicate yourself to just kind of being a part of this huge industrial complex thing that's going on. However, there are people that work with that complex but work outside of that complex, and they are the contractors. They make as much as most of the administrators in the railroad, most of the kind of the bosses and the managers do at the railroad here in North Platte. They make the same checks as them, but they don't have to deal with the unions. They don't have to deal with they don't have to deal with any of the garbage. Any of the politics involved, they don't have to deal with, because they're working for private companies, and they have better benefits, they have better everything, actually. But to work for them, you have to have an advanced degree in something that they need, and engineering is always one of those things. They need them in other things too, but engineering is a big one. So that's an interesting thing that works out nicely even here in North Platte. So anyway, the point is that there are so many different things that you can do in engineering, and many of them. Are we hearing people in Maxwell? Hello? Are those my engineering students in Maxwell? Well, either they're not or they just don't want to talk to me. Either way. But there are engineering opportunities here in Nebraska, even though it doesn't seem like there would be. And not just in agriculture, and not just in the railroad even. If we go back up here to civil engineering, or back down here to civil engineering, wherever it is. Where is civil? Are we in civil engineering? This is systems engineering, mechanical. Okay, back up here. Back up here to civil engineering. You have environmental engineering, which is something that you wouldn't think that we would have environmental engineers in Nebraska, since we're not one of the states that's considers themselves green, even though we're one of the greenest states literally out there. But we don't really consider ourselves. We don't try to cap everybody's exhaust or make everybody drive these high efficiency cars or anything. We just kind of think, oh, what doesn't matter. There's hardly any people here, so what's the difference? But municipal urban engineering is a huge part of any community, really, that has more than maybe 10,000 people in it. And so every city, every town that has a city council and a city building and anything else, they hire engineers to do their planning, and they don't always have them on staff necessarily. I don't think that North Platte. I think North Platte actually has maybe one engineer always on staff that they hire full-time. But if they need something else done, then they hire engineers to come in and do it. And so that includes everything from roads to buildings to plumbing to water systems to waste systems. All those things are designed by, maintained, and run by engineers in many cases, especially when they're first installed and first put in. And then maybe they're turned over to technicians after that. But they're always being updated. They're always being, worked on, and engineers do that work. So that stuff is happening in places like North Platte. Structural engineering is another place that is used just about everywhere. And here they're mostly talking about kind of big stuff earthquake, wind engineering, architectural engineering, everything else. But this one right here, architectural engineering, seems like a big deal, but it's required even in house building or garage building. So you have to build a house in North Platte, you have to have your plans signed by an engineer, and they have to approve it. And that signature costs, you know, a couple $100 just for that signature. And almost all of it goes to the engineer. If he's working for himself, all of it goes to the engineer. For one signature, they might spend 5-10 minutes looking at the plans and making some calculations for a simple home plan. The bigger the home, the more time they spend on it. But you know, $200 for 20 minutes, 30 minutes, not a bad deal. You have to realize that these kinds of engineers have a lot of overhead as well. So, but anyway, those kinds of jobs are available. They are out there. The big hardware companies and building construction companies like Menards, and Menards has their own structural engineers that work for them. And so you can go in and you can order, if you order all your equipment from them, like I'm building onto my house and I'm ordering my supplies from Menards, they signed my plans for free. So I didn't have to pay for it. They figure they're going to get their money back as I buy all my supplies from them. And it works out nicely. So civil engineering is something that just about every town has, and states and counties as well. The Nebraska Department of Roads, civil engineers, and they actually do internships. So if you're interested in doing an internship, we can connect you with them and see what they've got going. There's another civil engineering firm here in town that does things like roads and buildings. And if you're interested in an internship, we can connect you with them. So, you know, give me a call, or you can contact them yourself. If you're interested, we can look around out there and see what's available. I'm currently working with one student who wants to do a internship, and hopefully he's going to connect up with this professor across the street at UNL and do an agricultural engineering internship with computers, where they're going to be modeling the agricultural economy of Nebraska and the United States and even the world. And then I have another internship with an agricultural company they're doing water resources engineering essentially, and they are tracking how the water resources available, rain and irrigation and other things, are affecting seed growth. The water content in seeds. But anyway, so I got 2 internships going right now, and so I mean they're out there, they're available. These jobs are around, even out here in the middle of Nebraska. Okay, so that takes us all the way through 2.5 studies, talks about all these different types of engineering. They talk about the ones we've talked about, and they talk about a couple others like nuclear engineering and engineering technology and other things like this. And there are, of course, lots and lots of different kinds of engineering out there. They talk about engineering functions, different things that engineers end up doing in their careers, and the number of engineers in the United States. They have them numbered at 1,400,000 engineers in the United States in 2004. I wonder what it is now. I suspect it's probably going down. Let's check. Should they give us the website? Let's just ask Google. How many engineers in the U.S.? How many engineers in the U.S. And the one that they did, how large is the U.S. S&E workforce? National Science Foundation is a good place to check this. U.S. Science Engineering, FAS. So, let's see here. Science, so the S&E is going to be science and engineering. That's not going to be just engineering. So total S&E, math, engineers, right here, 1 million. Yeah, it's actually gone down. 1,370,300. And this is in, oh no, this is actually 1999. And this one here in the book is 2004. So it went up since 1999. So let's go look at let's see if we can find a newer one. What is this? This is 2010. Let's see. Wait, that's not going to help us. This is immigration. No, immigrations. Oh, here we go. U.S.-born individuals report having an engineering degree. It's kind of interesting. So, engineers, many of the engineers in the United States are not U.S.-born, so this will not be a correct number, I don't think. Yeah, these numbers are going to be all kinds of weird things. I'm not sure I'm going to really believe anything that comes directly from the government. They seem to be they seem to give us the information that they want us to hear. But let's see if we see a number that kind of compares to what they're counting here, which is number of engineers in the United States. Not talking about it, whether or not they're working or whether or not somebody's doing a good job as some politician or other. Let's see it here. Science and engineering occupations. So this one's another report telling everybody how good or bad the government's doing. That's not going to be very good. This one actually is probably a good one. This one is not government. It's the American Society of Engineering Educators. Number for 2012 on it. Let's see what it says. Females, engineering, faculty, doctoral degrees, more data. So the degrees, in 2011, 2012, so percentage bachelor's degrees, women, these are just degrees awarded. Excuse me. Goodness gracious, that's too much information. That's just degrees, that's not who are actually engineers. Okay, let's actually punch in there. See, here is the one that I was actually, the number that I was actually wondering about, or at least the report. It says that the U.S. science and engineering labor force stalls. So in other words, it kind of flattened out, or maybe even went down a little bit. It's different across different states, but overall it's stalled. Here's a number. Here's some numbers for us. So the percent of the total labor force, if you go back to 1990, when I was graduating from high school, it was low, and then it had a huge jump here, and it stayed pretty high for a little while, but now it looks like it's kind of just flattened out and maybe even dropping down a little bit. This only takes us to 2010, so in the 5 years since, what has happened, I wonder. My guess is that it's gone down, but I could be wrong. Hopefully I'm wrong. See what's happening to the foreign-born in the United States. It had a huge climb at that same time, as ours had a big climb. And then it's been pretty steady, and then you can see that there's a slight trend upward here in the past, 4 or 5 years. And up to 2010, and that has increased definitely in the past 5 years. In the past 5 years, the number of engineers coming from China, from Pakistan, from Eastern Europe, from all kinds of places, really. Russia, lots of them coming from Russia. So it's changing a lot. And the thing is that it used to be that when these foreign-born students would come to the United States, they would stay here because of the opportunities, but it turns out now they're not doing that anymore. The Chinese, for example, for the, back when I was starting college, there were Chinese people everywhere in the universities. And they were everywhere in the engineering department. They were everywhere in the math department. And they were teaching in the engineering, in the math department, the physics department. They were staying here and teaching in our universities. But they have so many Chinese people that want to do this now that there's no more room for them in the universities in the United States. We've filled all of our universities up with Chinese professors, and they've started building their own universities in China. And the Chinese universities are getting quite good, comparable to the United States universities. And so they're going back there to teach after they come here to get their education, because ours are still the best in the world. But that will change as theirs grow and get better and better and better. And the European universities have always been good, but they're seeing a resurgence in people going there. So there's a lot of things going on that are a lot of things changing in these fields. And the United States is struggling to keep up, to be quite honest. This is why we're trying to encourage people to get into this. So what do we need to do as students to get into these fields, to become a part of engineering? Of course, the first thing is education. But how much education do you need? How much education should you get? And where should you get it? So a kind of degree, the degree that you get is, I would say, pretty much the same across the board. Most engineers either get a bachelor's degree or a master's degree, or they go into a program that's a kind of a combination of the both. There are a lot of universities have a combination degree where you go to school for 5 years, and you go to school during the summers and you take some online classes and things like this, and in 5 years you get out with both your bachelor's degree and your master's degree in engineering. Because they found more and more that just the bachelor's degree doesn't really get you an engineering job for the most part. It usually will just get you a kind of a technical support job for engineering, and you don't get to really be an engineer. And engineers don't like that, so they go out and get a master's degree and they, finish it up and they go back to being an engineer. Should you consider getting a PhD? Well, it depends on what you want to do. I'm here at the American Society for Engineering Education, and many of the people that are members of this society, probably the majority of the people that are members of this society, are actually PhDs in engineering. Why? Because they are educators. So if you're planning on educating, working at a university, you probably want to get a PhD, because that's pretty much who they're going to hire. They're not going to hire anybody with a master's degree in engineering. Well, very rarely they will anymore. They used to hire people with master's degrees all the time, because there were hardly anybody out there with PhDs in engineering. So if you're interested in doing research at a university, or if you're interested in teaching at the university and doing research, definitely go for the PhD. Otherwise, I wouldn't recommend it. Otherwise, I would just not recommend it at all. If you want to go out there and get your hands dirty, doing things, fixing things, working on things, being a part of the research group, but not necessarily being the guy that's at the desk and going to all the meetings, then a bachelor's degree is probably just about right for you. You're going to make good money. You're going to have good, interesting jobs, but you're not going to be the man in charge. If you want to be the man in charge, I would definitely go for a master's degree. And then after your master's degree, I would go on and get what is called the professional engineering license. What do they call that? So the National Society of Professional Engineers, they just call it the PE license, I guess. The National Society of Professional Engineers is mostly for civil engineers, but it's not only for civil engineers. It was kind of started by civil engineers, but now a lot of engineers join this society and become professional engineers. But to become a professional engineer, to have your PE license, you actually have to take an exam, and it's more than one exam now, I think. And so let's take a look at this here. Let's take a look at what is a PE. To a client means you've got the credentials to earn their trust. To an employer, it signals your ability to take on a higher level of responsibility. So you essentially go through this licensing process, which is essentially exams. First thing is you have to become an engineering intern, and you have to get experience. So you have to actually work for an engineer with your engineering degree or just before your engineering degree, and start getting that experience and getting work under your belt. And then each state has a requirement for a licensure, for your licensure, and then you have to prepare for and take the PE exam. It's kind of like the biggest deal of your life. I mean, it can take months, even years, to prepare for the PE exam. And some people take it once, pass it, and get done with it. Some people take it several times and never pass it, because it involves a lot of different engineering disciplines. You have to remember a lot of things. You have to be able to do a lot of things, have a competency in a lot of different things, and you have to have a lot of self-confidence to get through this process. It's a major pain in the neck. My oldest brother, he did it, got through it. He's always been a very driven individual, very strong individual, did it just fine. I think it took him twice to get through it. My next oldest brother did it and failed, and still hasn't finished it. He's been out of school for a couple of decades now, and well, maybe about a decade. But anyway, he's really struggled with it and just decided it wasn't for him eventually. But it is a big deal, because once you've got that, then not only do you have this thing to kind of hang on your wall and say, I did this, but other people look at that and say, he is certified. So the people of the state believe in him because of all his work that he's done and the process that he's gone through. So anyway, the Professional Engineering Society is a big deal as you finish your education and get ready to start your professional life. All right. So now we are engineers. What are we going to do with our lives, right? Before we get into that too much, I want to point you at a couple of different things that you can do. Let's look at this right here. Actually, I don't know if they have a student membership here, but I doubt it. Excuse me. Yeah, I don't think they have a student license. Here we go, student membership in Nebraska. Right. If you're a student in Nebraska and you want to join the National Society of Professional Engineers, person holding a valid license to be registered professional student member shall be defined as a person who's enrolled in a full-time ABET accredited engineering program. So you have to be a UNL or UNO to do that, or Creighton, to join the Professional Engineering Society in Nebraska. However, there is something that you can join, even if you're in, it's free. It's called Engineers Without Borders. So Engineers Without Borders is kind of like Doctors Without Borders, and they do all kinds of global engineering projects for people all over the world to help them live better lives. And they do a lot of interesting stuff. And it's whenever I find a it's been moved. There it is. Whenever I find an engineering society that is free to join for students, I try to point it out, and I found this one the other day. So you can register to be a member of Engineers Without Borders, and I don't know exactly all the different things that you receive as benefits as a member of this organization, but let's see if we can figure out at the top of the page. Join now. Here we go. Becoming a member. Join a chapter. There is a chapter of Engineers Without Borders in Lincoln. Student chapter. Let's see, join the movement. How do we get to here? Oh, here we go. Student membership free for students currently enrolled in an academic institution. And you don't have to be, you don't even have to be in the engineering program, I don't think, to join this. So anyway, you create your little thing here, and you can. I think they'll send you newsletters on what they're doing and invite you to conferences if you want to go. And it's not a bad little thing. It's kind of nice to see what people are doing out there in the world to make this world a better place. And Engineers Without Borders certainly seems to be trying to do that. Actually, this took me to American Society of Civil Engineers. I wonder if that was free. I don't know. It might be. And not logged in. Anyway, there are places like that that are offering students free membership, which is, I think, great. Goodness, my computer is freaking out. So anyway, go look around. It's best if you want to join engineering societies. You're starting your education. Get online and use Google to search for engineering society of your particular kind. So if you want to do electrical engineering, do electrical engineering society. Search for that and look at the different societies out there. See if there's one that's either free or cheap to join as a student, and try it out if you want to. You get information, you get news, maybe even get scholarship opportunities. There's plenty of them out there, so I definitely recommend that. There's also specific engineering societies for women in engineering and ethnic minorities in engineering and other things like that, so not a thing to pass up necessarily also. So now that we've kind of talked about preparing to be an engineer through education, we now want to get into, here at the end of Chapter 2 and all of Chapter 3, and let's see, how many chapters are we doing? All of Chapter 3 before we start our test in how we do engineering. And that's essentially what we're going to spend the rest of the class on. We're going to now just get into how engineers do what they do, what different tools they use, how they interact with others to make things happen, and then we'll be putting those things into practice as well. So let's go to, this is chapter 2.9, and we're going to look at something on, where else? The fountain of all knowledge, Google. So, anybody know what Google means? It's short for the word Googleplex. Do you know what Googleplex means? The Googleplex is a number. The number is this number right here. 100.
Big number.
Raised to the 100 power. It is a big number. That's the word. That's what the word Google comes from. Very fitting, don't you think? So we're going to search for now something called the engineering design process. We're going to go to images, and we're going to look at many different ways that this is portrayed. The engineering design process is portrayed by different people. We'll start with this one. I like this one fairly well. It's not my favorite one, but it's decent. It's portrayed as a great big wheel.
Simple.
Very simple, very straightforward, easy to follow, easy to understand. And why is it a great big wheel? Because the process is a cycle more than anything else that really has no beginning and no ending. You could jump in this circle at almost any point, And you could jump out at almost any point. And engineers do it all the time. So let's say that we start at the top one, which is to identify the need and the constraints. So that's usually the place that we call the starting point of this process, but it's not always the starting point. It would be the starting point if you were trying to develop something completely new, from scratch. Identify the need. What is the whole purpose of this process? Is to identify a need that needs to be fixed or needs to be met or needs to be whatever, this need. And then to define some specific things that really bring this need into reality. Hello? Am I connected to Maxwell? Hello? I don't know what's going on. I'm going to hang that up. It drives me crazy. You're muted over there. Hello, Maxwell? Can somebody answer me? Okay, I'm just going to hang that up because it's just bugs me. I don't know why they're not answering over there or not. Call somebody, I guess, eventually. I should probably call somebody today. But anyway, it drives me crazy when those high schools don't do their part on their end. They just kind of figure I'm going to do everything. They can't do everything from this end. Anyway, so we identify what the need is and some of the details about it that kind of narrow it down to what it actually is. Because you don't want to say, well, we need to have better food. Because I don't even know what you're talking about. Are you talking about corn dogs are cheap and you don't want cheap food? Or are you talking about the food that comes to your house is rotten and it makes you sick? Or something else? I mean, you can have all kinds of different things that statement means. We need to kind of whittle it down, get to the nuts and bolts of what the actual problem really is, very specifically, and then go from there. We want to be as specific as we can without cutting out important things and use that to begin the process, if we start here. And then we go on to research the problem. So once we've got a need, we realize that there is a problem to be solved. And so we start researching the problem. Has anyone tried to do this before? What did we do when we couldn't solve this problem? How did we get around it before? What is the current methodology for dealing with this? Is there anything else out there that's not necessarily related to the problem that we have or the need that we have that could be used? Any ideas, any technologies that already exist, any whatever, anything else. And so you spend a lot of time researching, and that can be a huge part of this process. It can be a very, very long and grueling part of this process. It can last years even, depending on what you're doing. And then you imagine what you can do. You develop possible solutions. And you start planning some things. You select one of the possible solutions and start planning how you're going to use it. You start creating, prototyping, and then once you've got something that is really kind of ready to be tried, you start testing and seeing if it works. And if it doesn't work, you improve it. And then you're going to be back to the point where you're going to need to identify needs again. Because your process is going to take you around to a point where you may have a solution, you may not have a solution, you may have a partial solution, you may have a solution that you don't really like that much, you may have a solution that caused more problems and created new needs, right? And all of those things happen, sometimes all of them at once. Okay, you never have a perfect end to this cycle, and so it always goes on and on and on. And like I said, you can jump in at any time in this circle. Sometimes you're jumping in at the testing and evaluation part, where you already have a solution, and you're just jumping in and testing to evaluate to see if this really is solving the problem that you thought it was solving. Because sometimes that happens. And And then you get back to here and you're like, oh, no, it doesn't, and you start over again. Or you redesign it, or whatever you do. Or maybe you even re-identify the problem. Maybe you realize the problem is different than you thought it was. That happens all the time as well. So engineering is very much like this cycle, but like I said, I don't really prefer this one to others necessarily. It's a decent one. It's not necessarily the best one in my opinion. So let's look at some others. You can see that a lot of them have very similar types of formats. Let's look at this one, which is quite different. Here they have a definite linear kind of progression, and the top to bottom kind of progression. And this one, I think, is a little bit, I think this one's a little bit narrow-minded, that you're always going to start with a problem and you're always going to communicate results at the end, and there's going to be a beginning and an end to this process. But you can see that they also have this cycle going on through here. What I do like about this one is it shows that this cycle can go back to different points in the process, which is true. And you can see that it's essentially the same kind of thing. There's not much difference between this one and the other one as far as the content, but the way it's portrayed is quite differently. It does one thing fairly well and another thing very well. So it shows the progression well, but maybe the other one shows it in a better format for reality. But this cycle over here, I think, is more telling. That you don't necessarily go from point to point to point all the time. That you might skip back 2 points, or you might skip back 1 point. So that's another different way of representing this, but it's by no means the only way to represent this. Let's try another one. Here's one that has split path and arrows going both ways, so you can go back and forth through it, right? And again, that has its ups and downs of the way it's thought of. Let's see if we can find a really good one here. I'm usually able to find one that I really like. Sometimes it's the same one every year. People are coming up with new ways to do this all the time, so I like to kind of just look around and see what's new in the education world. It was an interesting one. Oh, that's kind of tiny. We'll just leave it how it is, the same size. Here you can see that this thing has this cyclic thing, but it has arrows going across the circle, right? Showing that you can jump around through this process in different ways. This one I actually kind of like, where it shows different cycles, different pathways, and then it has this kind of overall outline over here. That's not bad. This one is just confusing. I hate this one. You're just like, oh my goodness, what are you doing? Right? And of course, if you already know what you're looking at, it's not that big of a deal. So as an engineer, you look at that and you say, oh, that makes perfect sense. But if you're a student trying to learn what this is all about, it could really screw you up pretty bad. This one I like. It looks really complicated, but really you get the idea, don't you? You get the idea that this is a cycle, but there's not necessarily always the correct order. There's obviously an order that is ideal, and you can see that you can always go back to one of these things because there's ours going the other direction. But you can also see that sometimes you end up skipping around a little bit. And it's not necessarily that you've skipped a step in the process, it's just that you're using a part of the process to help with another part of the process. And then you go back to that cycle. So this one I really like, even though it looks confusing at first. This one's actually project management for construction engineering or something like this, conceptual design process. But anyway, I think it's a pretty good one. There's a better one out there that I've seen. I'm just not sure where it is right now. I haven't seen it yet. It used to come up fairly early in this little image cloud, but you just never know how it's going to work. See, these ones I don't like because the imagery does not show a process. It doesn't show any kind of process that you would normally just look at and say, oh, I know how that's going to work. Whereas this one kind of does. This one kind of shows that there's a circular thing, so you automatically assume that you've got to go around the circle, probably in a clockwise direction, kind of thing. But you get the idea, hopefully.
Well, there's one for you.
Which one? This one? Yeah, that's a mind mapping of it. That's not really a process drawing, unfortunately. Yeah, and I hate these ones. These ones are just totally terrible. This one doesn't look so bad, but it doesn't look like necessarily the design process. But anyway, the point is that the engineering design process is a cycle, but it is not a cycle that necessarily always goes the same way every time. Okay? I like this one too, where it has the circle, it has the arrows, but I would prefer that these arrows go both ways, so that you can show that when you get to a point in this cycle, if you have to go back, you can, and you should. But also, I would like to see arrows in between all of these, like we saw on that one, to show, and the arrows should go both ways, to show that at any point in the process, if you need to jump forward for a little bit, to do a bit of analysis, or to do a little bit of prototyping, or whatever it needs to be, that you can do that, and you should do that. And, you know, it's a little confusing to people at first to think, well, it's a process, it's a cycle, but it's not. It is important to realize that the ideal thing to do is to go through this cycle and to kind of go through it in order, as well as you can. But you also have to realize that the world is not ideal. And so you will not always be able to do things in the ideal way. The book has its own way of showing this in section 2.9. It talks about it a little bit in section 2.9. It doesn't really show you a picture like this, but on page 39 there's 10 steps of going through this process, like we just mentioned. And then it talks about how to be a successful engineer using this process. And then on page, let's see, then they go on to talk about traits of successful engineers and other things. They're all talking about just getting through this process. But later on in chapter 5, I believe, we're actually going to be confronted with our own version of this design method, which is on page 119. So in the next, for our next exam, we'll do this in more detail. We'll actually go through this process step by step and apply it to some different situations and learn how to use it. So, but we just give a quick introduction to it here so that you can be thinking about this, especially as we go into our first projects. So next time we will be doing chapter 3, next Monday and next Wednesday we'll be doing chapter 3, which is engineering ethics. We're going to talk about how you should behave as an engineer professionally, but also how you should take responsibility as an engineer professionally. And some interesting and useful stuff in there. And then we'll have our exam for chapters 1 through 3 next Friday, and we will begin our first project. So don't forget to send me your address if you're out, at the distance learning sites or doing this by podcast. Send me an email with your address in it if you haven't done that already, so that I can send you your kit, and I will send out those kits next week in preparation for our project the week after that. Have a good weekend.
Here's the homework for today.
Thank you, sir.
I'll see you in an hour.
Yep.